Hello students. In this video we consider the solution to this wave equation here, and this wave equation here with initial boundary conditions. So this is an initial boundary value problem, and in a previous video I solved this wave equation and I get a sine series solution for the spatial part, and then that's multiplied by a cosine of the temporal part. For the purposes of this video, I'm going to let a equal 1, and I'll let L equal 1, and then I'll impose a initial condition x times x minus 1. So if you didn't watch the video where I solved this equation by separation of variables, I encourage you to do so, and then you'll see what the form of the solution is like. All right, now we'll look at a specific example here. So we're going to solve this wave equation. So remember, separation of variables yields this function for each k. So that's what separation of variables gives us. And then if and I left it general without L equals 1 yet, so that you could refer to the previous video and you can see perhaps your notes or the solution I got for that video, so you can compare those two. All right. So then the Fourier series, remember, will leave these Fourier coefficients, the orthogonality conditions, will leave these Fourier sine coefficients, and then that leaves us with now the following solution, where I now let L equal 1 and A equal 1. So if you compare this solution to the solution from that previous video or your notes, and you substitute f of x is equal to x times x minus 1, and you let L be 1 and you let A equal 1, you should arrive at this result here. All right, so this will be for varying times. Now what I'm going to do in Sage is I'm going to set up this Fourier coefficient, b sub k, and I'm going to define a function to do that. So that's what this looks like in Sage. So I set up that cell. So you just hit Shift Enter to define that and put that into the cache, and then I'll define my series to be this sum. It's the Fourier coefficients times the cosine times the sine. So if you notice, this this term here looks exactly like what I have here for each term, and then I'm summing from k equals 1 to n. So this is going to be a partial sum. So I'm setting this up to be a partial sum. And then we, as we increase the number of terms in our sum, hopefully our solution gets more and more accurate. And then what I did here was I plot the initial condition, and then I add to that initial condition the plots of the solution at varying times. So the times I picked were time is 0.25, time is 0.43, 0.75, 1, and 1.17. I picked those times just for the picture purposes. I know they're not evenly spaced, but they will help us with the interpretation. So I add that. So P was the previous plot of the initial condition, and then I just iterate through this loop, and every time I add another plot to the previous plot of the next time in this list. Okay, and then I change the color, so I set up a color list here. So the first color will be black for the initial condition, and then when t is 0.25, the color will be red. When t is 0.43, the color will be blue. When t is 0.75, whoops, the color will be green, and so on and so forth. Okay, and then this n is just the indexing variable. Yes, I could have done the same thing here where I let p equal plus equal plot, but for those of you not familiar with this notation, I kind of left it like this. This n plus equals is the same as n equals n plus 1. All right, and then at the end I'm going to show p. All right, so we get the following plot. So let's take a look at this solution. U of x0, that's the initial condition, the top one, that's the black guy, that's the black curve here, and that is this wave right here, this part of the wave. So it's like we just set up the condition to be, we pull it down, like think of this as a string, we pull it down here and then we just let it go. Now at t is 0.25, the string starts to go upward, and then at time 0.43 it's still continuing upward, and then at time 0.75 it's above here, still continuing upward by the way. Then it gets to 1 and it reaches its max deflection here, and now at t equals 1.2, sorry, it's going to start coming back downward. And so it's going to keep oscillating up and down like this. So think if like you plucked a string, it would just keep oscillating up and down, up and down, up and down. And that we call a standing wave. All right, so that's the interpretation of the solution for the wave equation. Good luck.